Hey everyone, welcome back. This is Maddie. In this video, we'll be learning the types of case analysis. First of all, let me answer one question, that is, why do we need case analysis? The same algorithm can take different time depending upon the input size, input order, or input values. So instead of guessing, we analyze the case using three scenarios. The first one is best case, the second one is worst case, and the last one is average case. You may be a bit confused here. Case analysis and notations are different. They are not same. We can represent best case using all three notations: big O, big omega, big theta. We can also represent worst case and average case using all three notations. They are not one and the same. They are different altogether. Now let us see what is best case. Best case analysis is nothing but the minimum time an algorithm can take irrespective of input size n. And this analysis answers what is the fastest way that this algorithm can possibly run. Let's consider the real life scenario where you want to go to office tomorrow. The best case that could happen is no traffic. As soon as you reach the signal, it goes green. In this case, you reach office immediately, right? But the thing here is, best case alone is not very useful because it may never happen in real life. It gives the false hope. I hope best case is clear. Now let us see worst case. Don't worry if you have not understood best case analysis. We'll see that with an example. Then you can clearly understand all three different case analysis. Worst case analysis tells the maximum time an algorithm takes irrespective of input size n. Worst case analysis answers what is the slowest way that a particular algorithm can run. Let's consider the same real life scenario where you are going to office and that day you will be facing heavy traffic, and as soon as you enter the signal, the light goes red, and even in between the signals road is blocked. If that's the case, to reach office it will take the maximum time, right? So you always assume this worst situation and plan accordingly. That's what happens, right? We will always tell what if worst thing happen, right? You might have faced these things in any scenarios. You might have assumed what if worst thing happens, and you will be prepared for that worst thing, right? It goes that way. This case analysis is very important. Let me answer why. Because worst case analysis guarantees upper bound used in real systems and safe for performance promises. That's why most time complexities discussions are worst case. I believe this thing is clear. Now let us see what is average case analysis. Average case analysis tells the expected time that an algorithm can take over all the possible input of size n. And this case analysis answers, on an average, how fast will the algorithm run. Let's consider the same real world scenario where you are going to office and some days traffic is light and some days traffic is heavy, right? You calculate the average travel time over many days. That's how you plan some days, right? But why this average case analysis is always tricky? Because it needs probability and it is very hard to compute. And even the input distribution is often unknown. So this average case analysis is very less used in time complexity or space complexity. Here, one powerful sentence to remember all these case analysis is: worst case tells us what will not be exceeded, best case tells us what can happen, and average case tells us what usually happens. I hope now the difference is clear. Let us take an example and analyze best, worst, and average cases. I'll consider the example of linear search, wherein let's take an array and the target to find in an array. Let's consider array as these elements: 8, 6, 12, 5, 9, 7, 6, 8, 1, 2, 18. And the target here is to find the element 7 in an array. Now, how do we find where the target in an array is present? As per the linear search, we search for a target by checking each element in an array one by one from left to right. In this linear search, what is the best case that could happen? Let us see that. Best case. The best case that could happen is given target is found at the first index of an array. Let's take, we have an array 7, 6, 12, 5, 9, 7, 6, and so on. And our target is to find the element 7 in an array. The best case is we have the target element at first index of an array. And what is the time that this can take? Constant, right? Since we are finding the element at the first index, it is just a simple single comparison and finding out the target. So it takes the constant time. Best case time is constant time. And we can represent this as B of 1. Now, what is the worst case that can happen in this example? The worst case that can happen here is when the element is found at last index of an array or element is not at all found in an array. Let's consider we are given an array. I'll just consider the same example. Let me just copy paste this. I can remove this. Our array is now ready. In this case, let's consider our target is to find the element 18 in an array or the element 20 in an array. Using for loop, we will loop for each element in an array and reach at the end of an array after n comparisons, and at the end index we might or might not find the element. In that case, our for loop would have completed all the n comparisons. So what's the worst case time here? Size of an array, which is nothing but W of n, where n is the size of an array. We have seen the best case time and worst case time. Let us see what is the average case that can happen for this example. Can't we write the formula as all possible case time divided by number of cases. And this formula is applicable only for this example because the average case is very hard to find and may not be possible to find for all the algorithms. Mostly the average time for most of the algorithm will be similar to the worst case time. Now let's see the average time for linear search, which is nothing but for our current example. This can be written as 1 plus 2 plus 3 plus 4 plus up to n divided by number of cases, which is nothing but the size of array. Why am I considering 1 plus 2 plus 3 plus 4 and up to n? Because if the element is found at first index, it takes one comparison time, and if the element is found at second index, it takes two comparison time, and if the element is found at last index or not found in an array, it takes n comparison time. So I'm just adding all the comparison times here. Can't we just replace this with sum of n natural numbers formula? We can replace that with n into n plus 1 by 2 by n. This n gets cancelled. After cancelling, we'll end up with n plus 1 by 2, which is our average time for linear search. Therefore, average time is n plus 1 by 2, and we can represent this as a of n plus 1 by 2. Again, I'm repeating, average case is very hard to find and may not be possible to find for all the algorithms. And mostly the average time for most of the algorithms will be similar to the worst case time. I hope this concept is clear. Now let us try to represent all these three types of case analysis using all three notations. Asymptotic notations for each cases of linear search. Firstly, the best case. What was the best case time that we just now discussed? B of n is nothing but 1, which is constant time. And we can also represent this best case using all three notations. B of n can take upper bound of constant time. B of n can take lower bound of constant time. B of n can also grow exactly at constant time. With this, we can tell that we can write all three notations to best case and all are true and valid. Let us try to write the worst case for the same. What was the worst case time? For input size n, worst case time was n, which is nothing but linear time, as we have seen in our previous video. Now let's represent this linear time using all three notations. The worst case of linear search can also be represented as upper bound of n. It can also be represented as lower bound of n and can also be represented as theta of n, which is exact growth. And all these three representation are true and valid. Out of this, we can say that there is no fixed notations to represent best case, worst case, or average case. We can use all three notations for best case as well as for worst case and average case analysis. The last one is average case. In the similar way, we can represent average case using all three notations. The average case time was n plus 1 by 2. We can represent average case for input size n as upper bound of n plus 1 by 2. We can also represent average time as lower bound of n plus 1 by 2. Last but not the least, we can also represent using theta of n plus 1 by 2, which tells the exact growth of algorithm. I hope the difference between notation and case analysis are now clear, wherein we can represent all three different case analysis using all three notations. I believe this playlist was very much helpful for you to understand what is time complexity, what is space complexity, and how we can represent time functions, and what are all the time functions that are there to represent algorithms. And this video marks the end of algorithm playlist. From the next video, we will be starting with building up logical thinking, where we will be solving a lot of patterns using for loops. Thank you all for watching. See you in the next one.